Computers run on ones and zeros. That's a statement we've heard millions of times. But is it really that easy to believe that the world and all its data runs solely on two states? Let's start from the very beginning. Our ultra cool Instagram checking, video watching, music playing devices run on and process data using transistors. Transistors are tiny switch-like devices that are about the size of a virus but can control the flow of electric current. 1 denotes that current is flowing through the transistor, while 0 means that current is not. Your machine is nothing but an extremely large arrangement of combinations of these ultra-cool transistors. Now let's math this up. Right, so how do I say 12 with just ones and zeros? Or how do I say with just ones and zeros? In the units place, we have 0, 1, 2, 3 up to 9, after which we repeat 0 in the units place for the first time. Following which we repeat 1 for the first time in the number 11 and so on until 19. After which we repeat 0 but for the second time, aka the number 20. The same way, in binary you start with 0 and 1 and then you repeat 0 for the first time in the place of number 2 and then 1 for the first time in the place of number 3 and so on. But that's pretty tedious. But don't worry, there are much easier ways to convert from decimal to binary. But for those, we'll have to really understand what it means to see a binary number. In the decimal system, the unit place denotes that in the final number you multiply the digit by 1, the tens place you multiply by 10, the hundreds place by 100 and add them all up to get the final number. It's a simple observation that 1, 10, 100 and 1000 are all powers of 10. The same way, binary is representing a number in sums of powers of 2. Let's take 21 for an example.
What's 9 plus 10?
21.
So if you add 1, 4 and 16, you end up with 21 and these are all powers of 2. So this is how you represent it in binary. We can also try this with 36, which is nothing but 2 to the power 2 plus 2 to the power 5, which gives us 100, 100. And yes, it's possible to represent any number this way. Alright, but an even quicker way to do the exact same thing is simply dividing the number by 2 and looking at the remainder. Okay, so let's take 21 again as our example. 21 divided by 2 gets us 10 with the remainder 1, so we keep the remainder. Then our quotient is divided by 2 again, which gives the remainder 0. Then the process is repeated with 5, remainder 1. Then 2 divided by 2, which is 1 with remainder 0. These, when put together from bottom up, give us 10101. That's how numbers work in binary. Now it's time to break down the letters. If you were a computer scientist from the 19th and 20th century and you were asked to represent all the letters using numbers, you would quickly just label all the letters with their corresponding numbers and say bam, it's done. But then the question arises, how would you differ between a number and a letter? So we know there are 8 bits in a byte. So the first few bits will store the type of character typed and the next few will store the actual value. Prefix for smaller case letters is 011, while that for capital letters is 010. The capital letter B will be denoted with 010, 00010. Similarly, there are prefixes for numbers and special characters. Okay, so that's it for text, but what about all the rest? So the same byte that travels to the UTF-8 of your computer and gets converted to a character can also travel to the sound card or the graphics card and get converted to a sound or a color respectively. So now you can pass around chits in class with a bunch of zeros and ones of them and no one will have any clue what you're saying. We hope you found this video interesting. If you want to check out some more cool content, you can click here to watch a video chosen by YouTube's algorithm, or if you want to subscribe, you can click subscribe. We'll see you in the next video. Until then, good night, sleep tight, and don't let the CMX Lectilarious bite.